In order to implement a transformation in computers, we must tailor the equation to be used on vectors of data instead of continuous functions. So in this video, I'll introduce the discrete Fourier transform, which is a Fourier transform that's implementable in a computer, and walk through the derivation of an efficient discrete Fourier transform algorithm called the Fast Fourier Transform. And I'll also go through my own code and explain what I did to compute a fast Fourier transform. The Fourier transform is one of the most important algorithms in math due to the usefulness of frequency domain analysis. In my previous video, I showed the derivation of the Fourier series. Understanding the Fourier transform becomes much more intuitive if you think about it as a generalization of the Fourier series equation, which is this. The first thing we do is we rearrange the Fourier series equation in terms of the coefficients. So you can write it as the coefficient scaled by t, and then the right side is the formula to get each coefficient. Now, if we consider this equation in a more general sense, where it's not bounded by a time interval, so t becomes infinite, the first thing we should look at is what happens to the frequency term w naught. So w naught, the fundamental frequency, is 2 pi over t. Well, if t grows to infinity, then w naught approaches 0. And what was in the Fourier series, integer multiples of a fundamental frequency, now those integer multiples of a tiny, tiny, tiny number becomes a continuous variable. So we'll replace nw naught with a variable just w to represent the frequency spectrum that we'll be using. And additionally, our integral's bounds now will be from minus infinity to infinity. And so this is the Fourier transform equation. As you can see, w has replaced nw naught, and the bounds of the integral are from minus infinity to infinity. The discrete Fourier transform is one that is implementable on sample data. So from the Fourier transform, our input function FFT will become a sampled function, or vector x of n. And similarly, that complex exponential will no longer be a function, we'll sample that function. So we'll use capital N different samples. For little n ranging from 0 to n minus 1, we can sample that complex exponential. And k will be the different frequencies we can sample at. And k will also go from 0 to capital N minus 1. Just because of the periodic nature of complex exponentials, anything more would be redundant. You'd be recycling a discrete data you've already used. The integral from the Fourier transform is now a summation, and it's bounded by the length of the amount of samples we're using, so capital N. So if you think about it, the DFT is actually more similar to the Fourier series with a fixed length of n and a discretized complex exponential function instead of using a continuous complex exponential function. Looking at this equation for the discrete Fourier transform, the time complexity is one of the first things you want to look at. So for n equals 0 to n minus 1 samples, we have to do that summation for each frequency term, and k goes from 0 to n minus 1, so that's a time complexity O of n squared. And the key to improving this is realizing that this DFT can be continuously split into subsets of smaller DFTs, and I'll go through that process on the next slide. First, there's some properties to take advantage of with complex exponentials. So we'll substitute e to the minus I 2 pi over n with wn, so wn will be that equal to that. And now we can look at patterns in wn. So one is that we know these complex exponentials are periodic with respect to capital N, such that if we have something like wn times wn to the k times capital N plus n, we can factor out the capital N term because it just brings us back to the start of the unit circle. and we just have Wn Kn. There's also something called conjugate symmetry. I've drawn a diagram in the bottom right. Basically, any reflection in the real axis of a complex number gives its complex conjugate. And that sort of symmetry by reflecting in the real axis can be shown with this Wn. If the exponent is something like n, then the complex conjugate of it is capital N minus n. And so the result of that is if you have Wn to the k times capital N minus n, you can factor out the capital N term, and what you're left with is Wn to the minus kn. And as we know, that's the complex conjugate of Wn to the kn. This is something that's, if your input data going through your DFT is only real, then this conjugate symmetry is something that'll propagate through to your output as well. And so technically you can calculate just half of the DFT and take the conjugate of the output from your frequency bin 0 to n over 2 to populate the upper half. So to implement the fast Fourier transform, we start with the original DFT equation, and we're substituting here Wn in. Now we're going to split the samples into two sums, one for even indices and one for odd. And that'll give us something like this, where we replace the n variable with r, and in the even sum on the left, the math will just be using 2r's. In odd, we'll use in the odd sum, we'll use 2r plus 1 to give us 1, 3, 5, etc. Now in the even sum, we have almost what appears to be a smaller DFT of the half the size, except there's a factor of 2 in the exponent for Wn. Well, that factor of 2 can be moved to the base of the exponential's fraction. We know Wn is equal to e to the minus I 2 pi over capital N. If we had 2 at the top of that, instead of multiplying the 2 at the top, we can divide the numerator by 2 and have capital N over 2 in the numerator. And in that case, we just have W of n over 2. And so we can rewrite it as Wn over 2 to the rk. And that would give us a DFT of half the size. Similarly, we can do the same by factoring out Wn to the k from the odd term, the odd summation. And now we have two DFTs of half the size, and we can continue this pattern over and over again, log base 2n times, and that's going to give us a time complexity of n log base 2n. You just have to think we have log 2n splitting stages, and at each stage you have to do n multiplies. So in general, your formula sort of looks like this. You have your even of k plus Wn to the k times your odd of k. So here I've drawn a visual depiction of the FFT. This is a really common way of showing the flow of input to output through a fast Fourier transform. At first glance, you might notice that the inputs are arranged kind of funny. That's just the result of the continuous division into even and odd subsets that gives you this order of inputs. It's actually bit reversed order, as I've shown on the left. If you bit reverse the indexes into those inputs, you'll actually have something that counts from 0 to 7 normally. So the first stage, the length 2 DFTs are being calculated. The process to calculate a length 2 DFT is really simple because your W of 2 can only be 1 or negative 1. And when k is 0, it's always 1. So you have x0 plus x1. When k is 1, it's 0 when n is 0. So you have x0. It's 1 when n is 0. So you have x0. And it's minus 1 when n is 1. So you have minus x1. So in this case, like if you look at the top, x0 and x4, you have x0 plus x4, for your k0 term, and x0 minus x4 for your k1 term. You follow this pattern forward and then multiply the odd outputs by wn to the k. So for stage 2, that's actually wn to the 2k because you're using a wn over 2. And so you'd think you go from k goes from 0 to 6 in steps of 2, but from the formulas on the right, you actually don't have to compute for any k greater than n over 2 because it's just the negative of if your k is greater than n over 2, just subtract n over 2 and it's the negative of that. And so you only do half the complex multiplies and then use subtraction where you have your k's greater than n over 2. So that's why I only use wn to the 0 and wn to the 2 instead of wn to the 0, wn to the 2, wn to the 4, wn to the 6. And the same thing in the next stage. And then the result is you get your 7 or your 8 different frequency bins, so your frequency domain output. All right, so I have a program here that's going to calculate a fast Fourier transform. I'm going to generate the data using MATLAB and then implement the code in C++. So the MATLAB script I have here is going to use a variable n for the length of the data we're performing the fast Fourier transform on. I'll start with 64, but I'll go through more than just 64. So I set my input data to a cosine of the base frequency, 2 pi over n, and a sine of 5 times the base frequency, 2 pi times 5 over n. And I'm sampling this 64 times. And then I can plot this function using the MATLAB script. But the main idea is that I'm going to write this into a text file so that my C++ program can read it. So I'm going to write the input data. The other thing I need is my complex exponential that's also sampled. And so for that I use this here, e to the exponent 2 pi I n over n. So that will give me each point along the complex exponential that I need in my code. So I'll run this. And this is the frequency domain plot. There's a cosine of the fundamental frequency and a sine of 5 times the frequency. And this is a magnitude plot. And so we can see here, this is what the function actually looks like. And so we want our C++ code to produce a similar frequency domain plot. Okay, so let's go through the discrete Fourier transform class I have here. So for the Dft function, this is just the basic n-squared algorithm, and I'm going to use this so I can basically show the differences in time complexity. So in my main function, I'm going to run a Dft and show the time it takes to compute that, and then compare that with the start and finish time of the fast Fourier transform algorithm. As well, I have a method to compute the magnitude from the complex output, and some functions just to read the data from my MATLAB script and write back to my MATLAB script, because I'm going to use MATLAB at the end to compare the frequency domain outputs. One from the MATLAB FFT algorithm, which is, well vetted, we know it works, and then one from mine, so we want to see that the outputs are the same. So I want to actually just code this with you guys. So the first thing with a recursive algorithm, we want to have this sort of end case when we want to stop splitting up our DFTs, and that's when it's a size 2. You can also go until they're size 1, and then when you propagate them back, it'll run through your sort of main code, which would be down here. But the butterfly of a size 2 DFT is so simple that I just would like to stop the recursion there. So we'll say if size less than or equal to 2, then, and know that will never actually be less than 2 because our n will always be a power of 2. So recursively splitting it will eventually hit the size of 2. I'm using a two-dimensional array because the second dimension is used to hold both the real and imaginary components of our data because we know the Fourier transform output is complex. And I'm using just one array, and I'm going to populate this with the input at the start of my code. So in the constructor, I actually build the output data fast. That's the output of my fast Fourier transform, just by assigning it the input. And then I'm going to slowly build the output into the same array because as you progress, you can just sort of use previous data and then overwrite the data with the Fourier transform outputs. So I need a data 0 and a data 1 for the size 2 butterfly. So data 0 will be data 0, 0. We know at this point we only have our input data, and I'm running this Fourier transform on real inputs. Data 1 is going to be data 1, 0. So we don't have to access the imaginary part of the data array here because our input data is only real. Now we say data 0, 0 equals, we're going to now populate the data array as our output using what we just retrieved from it as the input. So we remember the Fourier transform butterfly when it's a size 2 DFT. It's just the complex exponential w of 2 to the nk. So here we have n0 and k0, so it's just 1. So we multiply the odd by 1, and it's just an addition. And the imaginary part of this is just 0 because we have real data at this point. And then here we have d0 minus d1. Here we have n is 1 and k is 1. N is 1 and k is 1 means w2 to the 1. W of size 2 to the 1 means e to the minus I pi, and that means negative 1. So we're subtracting the odd term from the even term. So for d1, that was the w1 term. On d0, the w of 2 term will always be 1 because n is 0 in the exponent. And then the same thing for the imaginary part of this one. And so once we do this, we want to return out of the function because we've computed our size 2 DFT, and now we want to return back to the calling function of this. Okay, so create the even and odd data out of the input array. So we're going to create two arrays, one for data even. We know it's half the size over 2, and it's complex. Data odd, size over 2, it's complex valued, so it has a real and imaginary part. Populate the even and odd data from the input array. Okay, so we're going to need to go through, our loop variable just needs to go through half of its, die is 0, I is less than size over 2, I plus plus. So our loop variable only has to go through half of its values because we're going to use that from my presentation. This is like R. I'll actually change it to R. Remember, for even, we're going to use 2R to index. So data even at R 0. So the real part is going to be the data 2 times I r, 2 times r, and the real part of that. The imaginary part of our data is going to be data at r1. That's actually just 0 again, because at this point we just still have our input array. Data odd at r, zero equals data at 2 times r plus 1 at 0, and data odd r at 1 is just 0 again. No imaginary part. At this point of our code, we are just splitting our input, and our input is purely real. Now we get to recursion. So we're going to want to call this function, which is FFT underscore recursive with, we'll do the first one on the even indexes, so data even, and now it's a half size DFT, size over 2. And similarly, we have FFT recursive data odd, and this is a half size DFT as well. Okay, once this returns, now we're ready to use our generic DFT formula from the even output and the odd DFT output. We know we have this wn variable multiplying the odd output, add the even output, and that gives us our x of k for whatever size Fourier transform we've returned back into. So we'll start with the for loop. So we're going through each frequency now to calculate this. So our frequencies from 0 to, interestingly, we can do size over 2. I went through this in the Fourier transform diagram drawing I had. You only have to do the lower half of the frequency variables, because the upper half can just be the negation of that frequency term minus size over 2. So I'll show how I do that in my code in a sec. K++. Okay, so when we index our W vector to multiply by the odd, we need to make sure we get that right. Our W index will be n over size times k. So why is that? If we think about our complex exponential, it is, if this is a n over 2 DFT we're computing here between even and odd, then this, if we're combining two n over 4 DFTs, 2 would mean n over size equals 2, and we want to multiply k by 2 because 2 would be the power in the exponent of our W. The even and odd index is going to be simply k. Yeah, I actually don't even need a variable for that. Okay. Wx odd at Wx odd. So this is going to be, because I only want to multiply this multiplication here once. So I'll do that at the start. So this is W times odd. And it's size 2. Remember, we have imaginary data now. This is a complex number, so whether the output of odd was real or complex, the output of the multiplication will be a complex valued number. So we'll do the real portion first. We're multiplying a complex number, W at its W index. The even part will be the even of W times the even portion of our data odd of our odd of the current frequency k in the even part, and then if we multiply the two odd parts together, square root -1 times square root -1 gives us -1, so subtract the value of those two numbers multiplied. W at W underscore index, the imaginary part times data odds imaginary part, and this will give us the real portion of W times odd. Okay, let's do the imaginary portion. So here we have W, the W index, and we're going to do crisscross. So the real portion of one times the imaginary portion of the other gives us the imaginary portion of the complex multiplication. So here we'll use data odds imaginary portion, and we're going to add then the opposite W index at 1 times data odd real part. Okay, and now we can implement our equation using these two outputs as the W times odd. So our actual data now at k, the even part is data even k, the real part, plus the W times odd at 0, its real part, and data k in the imaginary portion of this is going to be the imaginary portions added. So pretty straightforward for this equation, just because we've already done the complex multiplication, so there's just a sum. And then data k plus size over 2. So this is now exploiting that, exploiting the fact that the size over 2 factor in the exponent just creates a -1 multiplied by data k0, or sorry, multiplied by the W term on data k0. And so for these ones, we use just the negation on W times odd. It's just going to be, for these terms, negative of what it was for the k less than size over 2 terms. So now we subtract. Shouldn't say straightforward, because this is very complicated algorithm to understand. Requires a lot of knowledge in signal processing. It took me a lot of time to wrap my head around how this all worked. Okay, and now we've implemented the Fast Fourier Transform. This is radix 2, so the n log n is a log base 2 event. In my main function, you'll see I'm going to print the output to console as well as write it to my MATLAB script at the end. So if we run this, you'll see in my console here, error in my code. This was the real, this was the imaginary. Save that, run it again. I'll look here to the console. Yep. Same polls we saw from MATLAB. One at the cosine, which was at the base frequency for k is 1. this one's for k is 5. This one's purely imaginary because it was a sinusoidal, so it was out of phase. And you'll see this mirroring in the fast Fourier transform with real inputs. It's because of the complex conjugate symmetry of a complex exponential. So yeah, that's the gist of the code. You'll see also this time. It's more efficient than the ON squared algorithm, the DFT I run prior in my main function. I can also increase n, so I'll increase n next. So I just generated the data from MATLAB with n is 1024 samples now. And if I run the code, you should see the fast Fourier transform now be an even greater difference. So yeah, 0.1 milliseconds compared to 5 milliseconds. And a peak here, and a peak here. And these are really small values, so they can just be sort of discarded. Just slightly bigger than the filtering. I was using a threshold filter in my discrete Fourier transform for less than 1 e to the minus 3, but some of these are just very small, but not quite that small. So they still show up in the output. And then you can see the mirroring again. Yeah. So as our n grows, our fast Fourier transform algorithm outperforms the bare sort of brute force n squared algorithm, DFT, better and better. Of course, because it's the n is being scaled by log 2 of n instead of by itself. So as it grows, that scaling is more and more apparent. So now that the frequency domain plot that I do from the MATLAB fast Fourier transform, when I run this code on a data set of 1024 samples, I'll get a equivalent frequency plot. So MATLAB vectors start at 1, so 2 is 1 frequency bin 1, and 6 is frequency bin 5, so that's the cosine of the base frequency and the sine of 5 times the base frequency. And then if I run check data, I'm going to plot the C++ frequency domain data. And we'll see that my frequency domain from my C++ code is the exact same. Yeah. I'll put a link to all my code I've done in this video. Yeah, thank you for watching.